Right, so in this example, again, we're going to have to use some information concerning our results related to projectile motion. Okay, so I've copied some results that may or may not be useful up at the top. So let's get into the example. Well, what we're told is there's a catapult that launches a ball from the ground with the speed of 35 meters per second. The angle at which the catapult launches the ball is not known, so we have a scenario like this. Okay, it's being launched, we don't know the angle, and it's given an initial speed of 35 meters per second. Okay, so we need to be able to use this information together with the following. So we've used this is our U. Alpha's not known, but the ball is found to hit the ground 75 meters away, so this is important from the catapult. So it does the parabolic trajectory. This is an illustration. Simply, nothing is to scale here. It comes back down to the ground, and this distance, we're told, is 75 meters. So this is our building up the answer. So we have to show that there are two possible angles for the catapult to be calibrated in order to achieve this distance. Right, so what do we know? Well, there is a time, capital T, when, or T star, when the ball hits the ground 75 meters away from where it was launched. Right, so effectively what we know is some information that relates to actually this Rx component of our velocity vector. So what we know is Rx of this T, capital T, is equal to, on one hand it's equal to 75 meters. On the other hand, if I look at the formula above, then of course we have this formula to use. Okay, so this is U T cos alpha, which if we plug in what we know, this just implies we have 75 equals 35 and multiplied by T, T, capital T, T star, T star, T star, and cos alpha, where alpha's unknown. So the time this implies that the time, capital T star, when we end up at the ground is 75 divided by 35 times cos alpha. Okay, and this can be simplified further to give 15 over 7 cos alpha second. Right, so what? Well, we're still stuck because we still don't know alpha. But remember that at this T star, we've returned to the ground. At T equals T star, we've returned to the ground, so we know something else about the height. We return to the ground. And so vertical height when you're at the ground in our reference system is 0. And this relates to our second component, Ry of t, and this is what we'll use. So I'm going to copy this across. So this is our Ry of t. What do you know? I think we'll be copying more than what we need. Okay, let me just add a page. Right, and I'll sort out this just a second. So what we have is the following. We have, this is our Ry of t. Ry of t is equal to this. And Ry of t star should equal 0. And this gives us minus g over 2 t star square plus u t star sine alpha. So effectively what we have is the equation here. 0 equals minus g over 2. Now I'm going to factorise out t star because it's unnecessary to keep it in if it's a common factor. So I have this u sine alpha t star. Now our t star is 15 over 7 cos alpha. Okay, so what about alpha? Well, alpha is our angle that we're pitching it, the catapult, so that we have x and we have y. Alpha is somewhere between 0 and 90 degrees. Of course, if alpha is 90 degrees, you're straight into the old problems that we looked at, where what happens is the object is thrown vertically upwards, so you will not cover any horizontal distance, so it makes no sense to consider alpha equals 90 degrees. And when alpha is 0, you're just rolling the ball along the floor, and in which case what we have modelled doesn't apply. So what we can do then is I can simplify the above formula. So I have this. If I insert t star, I have the following. So why I'm mentioning alpha? Well, in this range, cos of alpha is not 0. Okay, remember the cos of 90 degrees, or if you like, remember that we're working in radians. I wrote 90, this should be degrees, or remember in radians it's 0 alpha pi over 2. Remember that cos of pi over 2 is 0, so this would create a problem for t star. Anyway, let's go on. So we have this, t star plus u. I promised I'd substitute in some values, so what we have is multiplied by 15 over 7 cos alpha plus, now initial velocity was, just to remind myself, 35 sine alpha. Okay, and then on the outside what we have is 15 over 7 cos alpha. Now if I ignore this because it's effectively non-zero in our eyes, I can divide through by this, and this just implies that we have the following equation. Let's see, and what else I'll do is I'll multiply by cos alpha. So I have 15 g over 14. If I don't mess up the arithmetic, so I have this, and now I've multiplied through by cos alpha, so I have 35 sine alpha cos alpha. Now remember here, remember this one, that this is actually 1/2 sine of 2 alpha. Okay, so effectively, so we don't need this, doesn't help. But we do need the other factor, as this can be 0 for a given alpha. Okay, so let me just move this down. What we have is, effectively then, what we have is the following equation. 30g over 14. So what I've done is I've multiplied both sides by 2. I should also divide by 35. Okay, let me tidy this up a bit. So multiply through the equation by 2 and divide by 35, so we get this. Okay, equals sine 2 alpha. Right. All right then. So, of course, this can be simplified to 6 over 7 times 14. Okay. So we have 6g over 7 times 14, 98, equals sine 2 alpha. Now, here's, you're probably wondering, well, where does the business of 2 angles come in? Well, let's set this equal to x, okay? So, set, or better still, set it equal to beta, because x I know we're using for other variables. So we set beta equals 2 alpha first, and we're going to come back to this later. So we need to solve this equation. Sine of beta equals 6g over 98. Now, if I just calculate this, so 6g should be around 60 divided by 98, which is good because after all, for this to have a solution, that right-hand side should be less than 1. So this is 6 times 9.81. If this is just to give us a rough idea, 9.81 divided by 98, okay, gives us the following. 0. is approximately, now we just keep this in our mind's eye, is approximately 0.600 or 601. So if we plot the graph of sine beta, so remember that alpha, I've said alpha has to be between 0 and 90 if we want this thing to be flung to the right and cover some horizontal distance. This means that beta is between, or if you will, pi over 2. Beta is between 0 and pi. So let's plot sine beta between 0 and pi and look at what we get. So what I have is the following. I have sine beta. I have this beta pi 0, and then I draw the usual curve. Or I try to draw the usual curve, okay? Now this is pi over 2, and this is 1. Honestly, this just simply has to be a sketch to give us an idea of what's going on. So we're interested in, we want when sine of beta equals 0.601 to 3 decimal places. So I can put this as a horizontal line on this graph, the right hand side. So if my 0.61 is about here, okay, so this is 0.61. So wherever this line intersects is a solution to our problem. So we have 2 solutions. Clearly this is going to give us 2 angles. So we have 2 solutions. And so if we know this, the first solution, beta 0, then we know this one simply by symmetry, because this will be pi minus beta 0. And that's it. Okay, so your calculator will give you this, and then you have to do some groundwork and get the second one. So let's return to the equation. I'm going to do everything in the exact form now. So this is sine beta equals 6g over 98, I hope. Yeah. Right, so my beta 0, the solution to this, the one that the calculator gives, typically it will give you the answers between, I think, minus pi and pi, minus pi over 2 and pi over 2. So calculator gives this. Right, okay, so I just need to step to one side and I need to calculate our sine inverse of 6g over 98. Good. So if you do this in the calculator with g, don't forget g equals 9.81 meters per second square. What you end up with is the following. Right, you end up with 0.6443 to 4 decimal places. Now, as usual, I am writing this for presentation purposes. However, in my calculator, I'm going to keep everything to full precision. So, right, don't forget that this is, let's call this beta 1. Beta 1. Beta 1 is pi minus beta 0. Okay, so give me 1 second. Give me 1 second. So this is pi minus this. Okay. Now, the other important point to make is you probably are wondering, what unit am I using? Well, of course, I'm using radians. So this is in radians. This is also in radians. And in the end, what I'll do is I'll just convert back. Okay? I'm going to convert back to an angle to give you a sort of physical meaning of the answer, and it should, hopefully if we've done the calculation correct, it should tie up that these two values are between 0 and 90, if I haven't made a mistake on my calculator. Okay, so remember that beta is 2 alpha. Beta is 2 alpha. Right, so this means that the alpha 0 will come from beta 0 divided by 2. Simply just, all I've done is rearrange this formula. So an alpha 1 will be, this is our second angle, first angle, second angle. This will be beta 1 divided by 2. Okay, so first I'll quote them in radians. So, right. Now what I'm doing is I'm taking the first value, I'm just dividing it by 1/2, I hope, to try and achieve the right answer. So I get this. Of course I should. So this is 0.32. 3221. It's a 4 dp. Remember that I am using full precision in the computer. Right, now the next one is, okay, just give me a second, 1/2 times this. Okay. So the next one is 1.2487 to 4 dp. Now, if we want to go back to radians, in degrees, then in degrees, this will just be, you multiply by 360 and divide by 2 pi. So in degrees, what you've got for the answer is as follows. So alpha 1, then let me just go back to this, okay, times 360 divided by 2 pi. Yeah, okay, gives me this, 18.457. to 3 dp. Again, I've used full precision on the calculator. The last one, what I need to do is I just need to multiply by 360 and divide by 2 pi once more, hopefully. And the last one, I get alpha 2. Okay, is 70, sorry, alpha 2. Alpha 1 and alpha 2, that's wrong. Alpha 0 and alpha 1. And the last one I get is 71.543 to 3 decimal places. Okay, where, again, I'm only presenting decimals for the presentation to a certain number of decimal places. But what I'm doing is using full precision in my calculation. So there are the angles in degrees. And that's it. So 2 angles between 0 and 90 will achieve a horizontal distance of 75 meters if it's launched with the speed of 35 meters per second from the ground with this catapult. Okay, so that's the end of this example. So I'll see you around for the next one.